So here's my investigation of an orange moving from rest, falling downward. So what I first did was I used Tracker to analyze my orange's different positions, as you can see here. And I was interested in examining what happens to the orange as it falls from rest. So I was using Newton's second law to help me investigate what its final velocity was and seeing how different forces contributed to a change in velocity of the orange. So I assumed a few things here. I knew that my final velocity was not my initial velocity, that the change of velocity was non-zero. And since I knew that the forces played a role, it has a relationship to the velocity, I knew also that my net forces were non-zero. And I was interested in looking at this change of velocity over the y-axis, which is shown here. These are the different positions throughout time, and as you can see, since it is curved, it means that there's not a constant rate of change. There's not a constant rate of velocity change happening here. If so, it would have been straight. So what I can do to understand why this function looks the way that it is, I can use the fundamental principle in a computational model. So I took a few initial conditions, knowing that my orange's mass was 0.07 kilograms, and starting it off its position at the position of my observed values, and then making sure that my velocity vector was 0, since when I started my video, it very much was the moment when the orange had dropped. So this value indicates that its velocity was 0 at this position. So what are some of the forces that are contributing to this? It is probably the weight force and the drag forces that are the main contributors. So to understand the weight force a little bit greater, we know that the weight force is a vector that includes its direction and its magnitude. Its direction is opposite to the downward axis, so that our downward axis here, the y-axis, is the j unit vector, and it's opposite to it, we use a negative sign. And then the magnitude is proportional to the mass, and its constant is near the Earth. So G is at 9.8, our Earth's gravitational field, and the mass is just the mass that we had indicated earlier, 0.07. So in code, this is what it looks like. We're taking all of our net forces to be the weight plus the drag force, which we'll talk about in a little bit, and the weight force, which is indicated by this variable W, will be the masses orange times the gravitation, so this is our magnitude, and then our direction will be the j hat, which we indicate by declaring this vector. So let's talk a little bit more about the drag force. The way that I indicated in my code was because we were suggested for this lab to look at drag force as it's proportional to the square of the object's velocity. So drag force in my model is the velocity, the vector velocity, multiplied by proportionality constant. So what this is saying is that the drag force is proportional to the square of the object's velocity as its magnitude, and as its direction, it will be opposite to opposite to where the direction of the velocity. And b is our proportionality constant, so that is needed because if anytime you have a proportional relationship, you need a constant. So how I chose my b value was sort of just trial and error, where I noticed that first my computational position was much larger than my observed position. So this is my observed, this is my computational. I tried other things, got more accurate results. Unfortunately, my graphs do not look that great. The orange here is just considering the model with gravity as our force, and this is our true data, and this is with drag force and gravity. The reason why I think this is because my initial position was not the same as my computational position, due to the fact that at my observed position, that was when my initial velocity was 0, right? But in my while loop, the first computation of my orange's position will include the orange's velocity, which is going to take in the net forces that we declared earlier, the mass, all these things, and update the velocity. So that means that the first orange's position is not going to be the same as what my observed values were, which means that they'll be different. And unfortunately, I wasn't too sure how to edit that in my code. I tried declaring the object's position first outside of the while loop and then having it run, but much to my chagrin, it did not work out. So let's examine this a little bit further, moving aside from it. One of the questions asked about terminal velocity. The terminal velocity is when the drag force is equal to the force of gravity, which means that the object's not accelerating, it's at a constant speed. And without drag, this is not a great, this is not actually my function, but this sort of gives me an idea of, just using this I can illustrate. I know that without drag force, when it's just accounting for gravity, it will be curved until it reaches 0. So it will look something like this beginning part, and then it'll bottom out with a slope of 0 from there on out. And then with drag, it'll be constant, much like this. It won't, with the drag, you won't see this curved part here, you'll see really this middle part where the slope is constant. So it'll be constant acceleration when we include a model that does have drag, because the drag force will be equal to the force of gravity at that point. So what if, one of the questions asked, what if the object did not start from rest and had a downward motion to it? So what I did was I chose the value of negative 2.87, sort of just because I wanted to take half the average velocity. Thought that would be a better number to choose. So there's that calculation, and when I included that, my graphs turn out to be like this. So once again, the gravity's still there, that's not changing, but this is the new model that accounts for initial velocity, and see how it's much worse of a predictor, because that's not actually how our observed data was. Our observed data I did not use a downward force throwing the ball. It very much did drop from my hand at rest. So that's what you see. A function that is under the curve. So that is all that I have to present to you.